Shown in the picture below is a saxophone. Part A asks us to circle the sketch that represents the node-antinode pattern when the saxophone is played in the low register and in the fundamental mode. Label that circle with the letter A. It's possible in your class that you didn't study the saxophone and its node pattern. In my class, I would have brought a saxophone to lecture and played it. What we learn about a saxophone is that the saxophone, since it is a reed instrument, involves having a closed mouth at this end surrounding the reed. That makes that a closed end of the node pattern. Then the saxophone is open either at the very end if all the keys are closed, or at some intermediate point wherever the first open key is located, and this is how you change the pitch of the saxophone by changing the length. In this case, what we find is that the closed open pattern in the fundamental mode will be this sketch. However, we can take a moment to analyze all of these sketches to see what their length pattern is. What we find is that in this lowest order sketch, the length is 1/4 wavelength. In the next sketch, the length is 3/4 wavelength. And in the one below that, which is here, the length is 5/4 wavelengths, and so on. This means that our understanding of a saxophone, or in fact any instrument that is closed at one end and open at another, typical example in a book is a closed or stopped organ pipe, gives us the relationship between the length and the various possible wavelengths as L is n/4 times lambda sub n, however with a caveat, and that is that n should only take upon the odd numbers 1, 3, 5, etc. Given this condition, we can then solve for the frequencies to say that frequency sub n is n/4 times the length times the velocity of the waves. We must keep in mind at all times with this formula that n can only take the odd values, 1, 3, 5, 7, etc. And then looking at a saxophone, we recognize that the saxophone itself is a wind instrument, meaning that the standing wave pattern is located in air, so that the velocity v is the velocity of sound in air, which we'll call 345 meters per second. Let's move on to part B. In part B, we're asked to determine the length of the cavity L, which would produce a note with a frequency of 116.5 Hz, which is a B flat. Since we're playing the saxophone in its fundamental mode, this B flat will be F subscript 1 for the fundamental, which will be 1/4 times the length, times the velocity of the waves in the medium, which is air. Plugging in what we know, we'll have a frequency of 116.5 Hz, an unknown length, but the velocity will be the velocity of sound in air, which is 345 meters per second. The only unknown in this expression is the length, and so solving for that, we get the result 0.74 meters. Part C asks us to circle the part of the saxophone that opens to make the saxophone play 1 octave higher. We stated previously that the saxophone in its fundamental mode is like a stopped organ pipe, so that it is open at one end and closed at the other. In the case of an organ pipe, the way that we make the pipe play 1 octave higher is we make the organ pipe open and open by unstopping it, thereby creating an n/2L instead of an n/4L formula. We do exactly the same thing with the saxophone. Looking closely at our image of the saxophone, we see that there is a small key located near the mouthpiece of the saxophone. This key is found here. When opened, this will create the saxophone to be an open-open cavity, and thereby change the mode pattern to be this one, which is the open-open pattern. This follows an n/2L, and therefore the frequencies are doubled. We'll label the circle surrounding the part of the saxophone that opens to create an octave as part C, as shown with the green circle, and then finally in part D, we're asked to circle the node pattern of the saxophone playing in the one octave up, not fundamental, but second mode, and that's found here.